So let's move into systems of linear inequalities. In the first 6.1, we talked about graphing linear inequalities, just one linear inequality on each Cartesian coordinate plane. 6.2 uses the word systems, and that means we're going to get more than one linear inequality on the same graph. So let's talk about this example here, and this is on page 306 in your textbook if you'd rather look there. It says a nursery school serves morning and afternoon snacks to its students. This obviously is pre-COVID. The morning snacks are fruits and vegetables and juice, and the afternoon snacks are cheese and milk. The school can accommodate 50 students or fewer, so we're talking about 50 or less. That's an inequality there. Students can attend for just the morning or for a full day. The morning snack costs $1 per student per week, and the afternoon snack costs $2 per student per week. The weekly snack budget is $120 or less. So, how many possible students can they have in the morning or for the full day and still meet this budget? We can see a couple different inequalities in here, can't we? If we had two variables, say M for morning students and let's say F for number of full day, we could then count that up. Now we know that they cannot have more than 50 students. So we can say that morning and afternoon students have to be less than or equal to 50. We can write that inequality. Now the snack part, we have morning snacks costing $1. So there's going to be $1 times every person that's there for the morning. Now the full day people will also get a morning snack, so we're going to have to add $1 for every full day student. Oops, I forgot the one. Plus the afternoon students, so the people that are there for the full day, their snacks cost $2. F, full day students. And that's for the week, right? And so that morning and afternoon snack cost has to be less than or equal $120. So you can see here how we can use inequalities to create these inequalities, or these restrictions, I guess we could say. And we've got two of them for this one problem. Let's move down here. We say systems of linear inequalities means that we are looking for the region where two or more inequalities overlap. So you can imagine shading the solution region for one inequality, and then shading the solution region for the second inequality, and where those solution regions overlap is going to be our answer that satisfies both inequalities. That is, the solution means that any ordered pair, or the coordinates, right, in that region, in the overlapping part, will work or will satisfy or will make all the equations in the system true. So when we look at this graph here to the right, Which part of this graph on the right is the solution to both the linear equations graphed? Well, you can see it's the overlapped part. I'll grab my crayon. A red will show up, and you can see that this region here is a little bit darker green. This is where the two inequalities overlap or cross over. And so we can say that it has solutions that satisfy both inequalities. Let's look at page 307, or you can do that on your own here. And we're going to do together, or I'd like you to think about, if you're at home, the answers for page 307, number 1A, B, and C. If you're working at home, please check your answers or what you're finding in the back of the book. This key ideas page, again, is straight from your textbook. Just a few things to highlight. All of the inequalities in a system of linear inequalities are graphed on the same coordinate plane. The region where their solution regions intersect or overlap represents the solution set to the whole system. That means all the inequalities that we graphed. Also, if we scroll down just a little bit, okay, when I went back and listened to myself, you can tell that I'm eating jubes. Sorry about that. The last thing I want to mention here is if the solution regions for the linear inequalities in the system do not overlap, then there is no possible solution to the whole system. There's no coordinates that would work in both the inequalities. Okay. So 6.2 introduces you to the idea of systems of linear inequations, and 6.3 lets you practice. So let's look at them together. I mean, both of them at the same time. What conclusions can you make then about this system of linear inequalities on this graph that's to the right? Think about it, and then we'll discuss your answer. You can pause it if you want. So we see that there's two lines. We've got one boundary line here that's been shaded less than y, or here solution region is below the line. And then we've got a second boundary line here, and the solution region has been shaded above that line. So we see that the solution set, or the overlap here, is going to be this part. This yellow part are the coordinates, or the ordered pairs, that would work for both these inequalities. Now, it's important to note that the boundary lines are solid, right? So the boundary lines are also solutions that would work in both inequalities. And we see the point of intersection of the boundary lines. This point here is both solid lines, so that point would also work in both inequalities. Let's flip the page. Let's try this one together. A company is making two types of boats on two different assembly lines. They're making aluminum fishing boats, and they're making fiberglass bow riders. Okay, there I inserted a picture of an aluminum fishing boat so you could tell the difference. I think the Lund company makes both these kind of boats, probably other boat companies as well. So the question here, when both assembly lines are running at full capacity, a maximum of 20 boats can be made a day. These boats together, both kinds, only 20 can be made. The demand for fiberglass boats is greater than the demand for the aluminum boats. So the company makes at least 5 more fiberglass boats than the aluminum boats each day. The question is, and this is a realistic question that companies would hire statisticians to find the answer for, because of course companies are not going to waste their time creating boats or whatever they're making if there's not a demand for them. So this is a real question. What combinations of boats should this company make? So let's set this system of linear equations up. Let's let A equal the number of aluminum boats to make, and F equal the number of fiberglass boats. So again, in any of these words problems, you're going to notice there's two different categories, and you need to give a variable to each of them, a variable that makes sense. Okay? Now, let's look at this first bullet and try to write an inequality from that first bullet. So it says maximum 20 boats can be made in one day. So we see that A, the number of aluminum, plus F, the number of fishing, have to be less than or equal to 20. Okay, the number of boats made. When we look at the second bullet, it contains our second linear inequality. So we know that 5 more fiberglass boats than aluminum boats will be made. Now, often in a wording like this, what's a lot easier to do is make an equation first. So, if I'm comparing the number of aluminum boats to the number of fiberglass boats, I know that there's going to be 5 more fiberglass. So if I want to write this as an equation, I know that I need to say aluminum plus 5 is going to equal the fishing boats. Just think about this for a second. There's going to be 5 more fishing boats. So in order to make an equation or make them equal, I need to add 5 to aluminum. Now, we know we're not asked to make an equation. We want an inequality. So I'm now going to erase the equation, the equal sign. Having the equal sign there, though, helps us in writing that inequality. Now, we need to make at least 5 more. So the fishing has to be greater than the aluminum plus 5. Now that we have our system made, we can easily graph these. You are good at this. We are going to find or put them both into slope-intercept form. Then we can plot the B, and we can graph both systems and find where they overlap. The only thing we need to do is to decide which variables on the x-axis and which variables on the y. It doesn't really matter as long as you're consistent and do both the same for both inequalities. We didn't talk about it before, but when we're dealing with real life problems, we're not going to have the negative coordinates. So we really only need to draw quadrant 1 here, like this. And let's put A as our x, our horizontal axis, and F as our vertical axis. Okay, go ahead and draw these two inequalities. You know this is discrete, so I'm going to shade this orange, and we know that we're not including decimals. We can't have a small amount or a half of a fishing boat. Okay, this will be totally orange. And now I'll graph the second inequality, and we see that F has to be greater than that boundary line. So I'm going to shade. Again, it's discrete. Sorry. So I'm going to use also a form of orange. You can't really see where they overlap. That's too bad. I'm also coloring in this solution, or this section here. Okay, so that's this color. And now we can see where our solution lies in the overlapping part. So let's think of some options, the amounts of aluminum and fishing boats. So we realize that any ordered pair within this overlapping zone will be possible solutions. And we can check those solutions. So I've identified 4 possible solutions, or ordered pairs. So, for example, 5 and 13 together, that is 18 boats. So yes, that's less than 20 in a day. And are there at least 5 more fishing than aluminum? Yes. Let's do a few more examples on the next video.